Hey guys, this is going to be a different kind of video to what I usually do. What I've done is I've pre-recorded the content so that I can just narrate it and talk over the top of it. This should free us of the annoying click sounds that I get a lot of comments about. And I also want to preface this by saying this is gonna go pretty quickly. We're doing it at double speed, and we're going to cover a lot of content. So let's get to it. Here we're just starting with a cylindrical point because we're going to be creating a circular sort of mesh. So by default we're always going to use values of pi for that. 0 to 2 pi, that's our entire range of the circle. And now we're also going to grab another range component for our radii values. And so I'm also using binary values, so 2, 4, 8, 16, 32, so on and so forth, just because they play a bit nicer with divisions. And now I'm just going to create a remap range for my inner and outer radii, which you'll see in just a second when I zoom out. There we go. And so I'm grafting that value as well so that the radii cross-reference the the angle values. And so now we're going to use the graph mapper to get a bit more control over our simulation, and then we're going to create the mesh. And so obviously when we're creating the mesh, always flatten the points coming in, and then we need a U count and a V count, which is going to always be the amount of values in a range plus 1. And then I'll plug these in, and I think I plugged them in wrong. Yep, so I waste a little bit of time here just changing them around, but eventually we'll get it right. And there we go. Okay, there we go. Sorry. So now the mesh is correct. Everything's working. We have control with our Bezier handles. And I'm dropping down a Kangaroo 1 solver because I still really like Kangaroo 1 solver. So we need to set up our springs obviously, and we also need to set up the simulation, so our button, our time result set up, and now we're going to do something a little bit different. We're going to create warp and weft lines with this definition, which means we're going to be able to exhibit a lot more control over the simulation, because we can actually change what the mesh is doing in each direction. We could give it more tension across the U direction or less tension across the V. These are all things that are sort of open to us. But for the time being, I've just used the normal mesh edges just for the base simulation. And then what I'm doing now is I'm list iteming out the first and last items of each list to give me the naked edges, or the naked points, sorry. And then I'm going to use this little function here to create a cull pattern. And because I've done it based on binary numbers, or anything that's 2 to the power of some value, I can cull away the points I don't want in a really nice way. And you'll see how that works in just a sec when I preview this off. So we have 2, 4, 8 points now in the simulation, and these are going to be my anchor points. Reset the simulation, and we've got base simulation going, plug the mesh in, and we're away laughing. Okay, so we'll preview that off, and we'll preview a lot of the other geometry off. Okay, simulation works, good start. So now we're adding in the unary force, stock standard component that I use in virtually every Kangaroo simulation, and we're going to use a merge node for our forces. Very key. It's just a really tidy way, I think. I was talking about this in the last video. Much better to use a merge node. Okay, and so gravity, I'm going to overhaul gravity because I want a greater effect in this simulation. And so now I'm just going to connect in the length parameters, for the rest length parameters for these for the simulation, and I actually make 2 mistakes here because I'm doing this. on the fly, and we'll see what those are in a sec. For one, I accidentally plugged the value into the stiffness, not the rest length, and I also ran it over polylines. So with the springs component, you can't do it over polylines, and it has to be over individual line segments. So in a second, I'm going to figure that out, and I'm going to drop down 2 explode nodes. So we'll just wait for that to happen. Just checking to see what just the whole debugging process. Simulation clearly isn't working. What's going on? Oh, yep. Good job, Daniel. You need to explode them. Okay, so we explode them. Reset simulation, and it's all working. But I also notice here that the stiffness is plugged in, the rest length is plugged into the stiffness, which is not helping. So I'm gonna quickly change that in a sec. There we go. And now we're going to do something a little bit different with the Bezier control handles. We've pulled out another graph mapper, and what we're going to do is we're going to map this to the stiffness of the of each line segment, or each group of line segments. And so I need to graph this so that it relates to each branch index that I want. And so what I'm trying to do is I'm trying to make the exterior edges stiffer and the interior edges a bit more flaccid, for lack of a better term. And this will have some really cool effects. You can see that the closer to the outer edge, it holds a bit more taut, and the inner edge is a bit it's a bit more jellyfish-like. I think that's a metaphor that I used in the last definition. And so now we're also going to, okay, so we've set up the stiffness for one direction. We're also going to do the same for the other direction. And key thing to note here is that the number of lines is going to be equal to 1 less than the number of points, because two points make one line. And so here I'm just checking that my branches line up. You can see I have 16 branches in each, and then I just had to flip the matrix going in there, and you can see, there we go. There's our simulation automatically coming into play. Now the middle, or the center, the pieces closer to the center, the edges closer to the center, have a lot more fluidity in them. They hang a lot looser, which is something I haven't really seen a lot of people try and do. So I thought I'd show how we do this in a tutorial. Okay. And so now what I'm going to do is I'm also going to add in some sort of exterior springs into the simulation. And this is also something I don't think I've ever seen anyone else do. At least correct me if I'm wrong. But what you can do is you can plug multiple different kinds of geometry into your simulation at the same time. So I'm going to have meshes and polylines running into the simulation, which means that these edges, or these curves that I'm creating on the perimeter, well, I'm no longer going to be anchoring the mesh. I'm going to be anchoring the curves, and that way the mesh is completely in suspension. And obviously it looks a bit confusing at the moment, so I'm just going to throw down a merge node and merge all the geometries into the geometry tab. And obviously I've got a mesh going, so we can't see the output properly, but now we'll preview that off, and you can see there are my polylines. So really quick, a really easy way to do it is take a line, divide it up, and then create a polyline through those points, and that gives you a more accurate representation of a rope or some sort of bungee cord or something, and the way it would react. And obviously we have to create a separate springs simulation for each and every element that we bring into the simulation. Okay. And so now, what are we doing now? Okay, so at this point, what I also want to do is I want to add some rotation into the original mesh, or some rotational offsets. And so I'm dividing the uh, range 0 to 2 pi, so 360 degrees, by the amount of divisions, which is 32 in this case, and then I'm multiplying it by several things. I'm multiplying it by an integer, so I can sort of offset each curve from the previous one as much as I want. And we'll see how this works in just a sec when I plug it in. And we'll just need to preview this on. Yeah, so you can see we have rotational control over we can do incremental controls, and we can also, when we pan down in a sec, and add the slider in, we can do control based on integers, so whole multiples of the rotational distance. Okay, and now what I also want to do is I want to add in a second line of control, or a second line of ropes or something based on another closer position into the center. So this one, I'm not going to. Well, at the moment I'm building it with a line with start direction and length, but we're going to change that in, I don't know, very soon. And what this is going to allow me to do, well, I want a bit of that rotational component in the final mesh. So I'm going to build a new line component, and I'm just going to scale the points in, and I'm also going to move them downwards. So we're going to move them in a negative z direction, so that they're closer to where they are in the endpoint of the simulation. So I move them down. Nope, you need to plug them into your line, and then plug that into the division. And then we'll also have to grab our endpoints and merge them into a new node for all the anchors that we're going to create. And that should be happening soon. Yeah, here you can see. So I've taken the anchors from the outside curves and the new anchors, reset the simulation, and there we go. We're getting a bit of a strange result. And so this slider here allows me to pick any, how should we say, any row of points that I want within the entire simulation. Okay, and so now once again I'm just setting up the spring length for that as well. And there we go, we now have a working version of it. And you can see at the moment it's on the exterior, which probably isn't what I want. So this is something I'm just going to change in the simulation as well by scaling it in. And now we're going to start to do a couple more interesting things. And yes, you can't scale anything to 0. This is something I find out quite a lot. I always forget this, but yeah, you can't scale by 0. That doesn't mean anything in Grasshopper and Rhino, unfortunately. You can in other programs like Max and Maya. I wish you could in Rhino, but you can't at the moment. Okay, and so now we're going to add in a rotation component. And actually, what I like to do when I'm doing multiple transforms, rather than stringing them into each other, you can do what's called a compound transform. So you merge several transforms together, and then you basically transform all the geometry once by all the transformations at the same time. You can do this with any number of transformations. You just need to watch the order in which you add them in together, especially if they're on different planes and such. This works well because they're all using the same plane of reference, so I can do my move, scale, and rotate all at the same time. And you can see I keep setting that to 0 because I think it's really fun to do. Okay, and so now what we're going to do is we're going to try and build some animation control straight into the simulation without me having to really tinker with any of the parameters. This is something I did once in my wave simulation tutorial, where we're sort of going over another way to do it again. So I'm just creating a rotation based on the counter coming out of the simulation reset. So you can see we can get some really nice rotation going, which I don't even have to touch at all. It can just run all on its own with the counter component. And then we're also going to set these up for the move and for the scale as well. And so for the rotation, we only, because rotation goes in a circle, it can just continuously loop and loop and loop. But the scale, we can't, if the scale gets too high, then we're just being a bit absurd with our geometry. So what we need to use is this modulus function, so that its modulus can kind of bound it to a certain range. But what I'm going to find very quickly is that modulus is still not doing the right thing that I want for this simulation, because it's going to give me a hard reset every time it goes to 0. So what I'm actually going to end up doing, you can see that that's way too jerky for what I want to get out of the simulation. So what I'm going to do in a second is I'm going to use a sine wave, because sine waves are sinusoidal. They go up and they go down and they do it smoothly. So I'm probably just going to use this for my vertical move, because I think it kind of works for the move. It gives us this weird sort of heartbeat type feeling, which I'm not sure if people are into, but I thought it was kind of cool. So now we've just paused the simulation so we can create our next control. So sine of x times y, so that we have, because we're going to be using the counter once again for our x value, and then the y so that we can control the amount that it's, or the frequency of the function. And so once again, it's way too quick at the moment. We really need to hone that in. And I've also added in an amplitude parameter at the beginning. To be honest, I think I should have slowed this down a lot more, but apparently I was happy with it at the time. So it's doing its thing at the moment, and it's kind of a funky simulation. There we go. Now we're getting something a bit more interesting. We're getting this weird sort of how do we call it? Sort of periodic motion. Okay, but now now here's a thing that happens. The simulation at the moment is going to break because we need to set up some initial values for each of these move, scale, and rotate functions. It's not going to work because I think the issue here was that the when the counter is reset to 0, obviously that sets our scale to 0, and that breaks the entire simulation. So what we need to add, I'm going to figure this out in a few seconds. I'm going to need to put in some more expression components. So at the moment I've just reset it back to what I had before, with all these sort of default values, and you can see the simulation works. Okay, and so now here we go. So if this is going to change to true, return y, otherwise return z. So when x is true, that is when the simulation is being reset. So this is going to be my default value, and then the expression that I created before is going to be my value for once the simulation starts running. And then I'm going to do this again. I'm going to make another, I'm just going to copy and paste this Boolean expression and then connect these up. And actually what I should be doing is not connecting up the Z transformation on the left side, but rather on the right side. There we go. Fixed that. Made those connections. And now I need to do one more for the rotation as well. You can see this is what I really like about this is I'm really showing my entire process from sort of start to finish, and that's something I don't think I've shown all that often. Like this is a lot more of how I work and how I actually work things out on a sort of day-to-day basis. It's not all just fluid as my tutorials generally are or try to be. Okay, and so now what we're also doing is we're adding in, we're messing with this control for the what's it called? Well, actually, we're not adding it in. Now we're just messing with parameters. And what I was doing there was showing how you can sort of subset the range of the simulation. So we don't need the entire 0 to 2 pi or 360 degrees of geometry. We can cut it back if we want. And now I'm just going to do a bit of tweaking. I'm going to turn all these wire displays to hidden just so that it's decluttering my definition a bit, because you can see it's gotten pretty messy. And so yeah, so now just more tweaks on the actual geometry. We're going to turn the simulation on to see what actually works, what tweaks actually look good. So we can see that this graph mapper isn't doing too much, but this one has a lot more control, probably a lot more than I was expecting, and then this one also. So and those are the two graph mappers that are controlling the warp and weft directions and the stiffness of each of those components. And then obviously we're just going to do a bit more tweaking here so that this rotation is a lot slower. Or is this the scaling? No, that was the rotation. This is the scaling. Obviously I'm not happy with how much it was scaling at the moment. And then what are we doing here? Oh, I just completely disconnected the move because apparently I didn't like it that much. But there we go. We'll reset the simulation. Yeah, so when you change the point count for either of the springs or those tensioning cables, it's going to break the simulation. So we need to do a hard reset every time we do those. And that's basically the entire definition. Hope you enjoyed it.